In this experiment, we'll look at the interactions of light and atoms, as well as interaction of light with diffraction grating. This is a three-part experiment. So the first part will look at diffraction of light, treating light as a wave. The second part will take a look at the experimental findings that led to theories of light beyond just a wave, theories of light as a particle. Namely the photoelectric effect. And then in the last part, we'll look at the discrete energies that atoms emit when electrons are excited and relax back down using a spectroscope. And so the first part of the experiment is going to be, an actual experiment. The second part is more of a simulation, and the third part is also experimental. Okay, so let's get into what's happening in the diffraction grating part of the experiment. So you will be given a laser pointer of a specific color, and the color is tied to a specific wavelength that is put out by that laser pointer. And so you're introducing a specific wavelength of light onto a diffraction grating, and this laser pointer is supported as well as the diffraction grating, and then you'll be using the whiteboard as a screen in the background to see the pattern of light spots that appear after the diffraction grating causes diffraction of the incoming light beam from the laser pointer. And so that is what these points are to represent. So this is kind of the macroscopic view of what you're doing, and skipping over to kind of more of a microscopic understanding of what is really going on here. We have an incoming wave of light from the laser pointer, and it hits the diffraction grating, which has these little tiny holes, and the holes are spaced out at a specific distance d. So I'm just going to go ahead and say that from here to here is d. We know we're passing a specific wavelength of light, so I'm going to go ahead and label that as lambda for the wavelength. And when it passes through the holes in the diffraction grating, it causes there to be a new wave formed at the opening of each hole. And as these new waves continue on the other side of the diffraction grating, parts of the waves will overlap, and that overlap becomes more extreme as they go out from their initial point. But that leads to a phenomenon of constructive and destructive interference. And so the points where you see a spot of light is where there was constructive interference. So the waves essentially added together. And the points where there's no light would be considered a region of destructive interference. And so you get a pattern. It's essentially the waves canceled out in that region based on how they interacted with each other as they were moving towards the screen. And so you get a neat pattern of light spots, and we can actually use the distance between light spots and the distance from the grating to the screen. So we'll actually measure this as well. We'll use that and the distance between the light spots to be able to measure essentially and calculate the distance between the diffraction grating holes d that we already established. And so the relationship is also dependent on the angle involved between the two spots. So we'll label the angle theta. And the formula that relates all of these variables is n times the wavelength equals d, the distance of the diffraction grating, times the sine of theta. So we'll use some trigonometry based on the distance between the diffraction grating and the board, the distance between the spots, to determine theta, and we'll be able to calculate a value for D. That will be our unknown, because we do know the wavelength that we're shining based on which color laser pointer we're using. So you can plug in a value for lambda, plug in a value for theta once you've calculated that from your measurements. And for the purposes of this, we'll actually ignore n. N is just an integer, so we can let it be 1 for the first spot away from the center spot. And so we can solve and find a value of D. All right, so that's the first part of the experiment, and this is looking at light as a wave. In the second part of the experiment, we will look at the classical experiment that kind of not exactly debunked, but changed the view of what light was, from being just a wave model to now we understand that there is some particle nature to light as well. So this uncovered the concept of a photon as part of the model of light. So it challenged the theories that already existed on what light was and led to theoretical explanation of light as involving photons. So in this type of experiment called photoelectric effect, it was observed that when light of a specific frequency is shown on some sort of metal surface, electrons can be ejected from that metal surface. And so that is what's being represented here, light shining on the metal surface and some number of electrons being ejected out of the metal because of the incoming light. And it was found that these ejected electrons depend on the frequency of the light, but not on the intensity of the light. So that led to some theory that there must be particles with discrete energy in the light that led to this ejection of particles from the surface. So you'll look at a simulation to determine what the voltage required in order to get a specific metal to eject electrons would be. All right, and in the third part of the experiment, what we will be doing is using these devices called spectroscopes, which generally have this kind of shape. The ones that we have are blue plastic devices, and you have a spot where you can look in over here. So I'll just draw this like it's your eye looking in. And light comes in from this little gap on the side, and it reflects off of a sort of a mirror, but it allows there to be splitting of the different colors of visible light, and they will split in a way that they land on the correct part of the scale on the far side that corresponds to their wavelength. So there's a scale over here. So when you're looking in, you can see the scale and you can see a line. So this is what it would look like when you're actually looking through there. You'll see lines corresponding to different colors of light, and you'll actually see the colors of light. So you'll be able to say, okay, the red line is at 690 or whatever wavelength, and you'll record these values based on the scale according to the correct number of significant figures based on the number of lines between each nanometer measurement. So you'll measure wavelength in this way. You'll record a value for each colored line that you can clearly see, and this actually corresponds, the color / wavelength of the different lines corresponds to a change in energy for an excited electron in whatever atomic emission you're looking at. So if you're looking at a hydrogen lamp, these would be the atomic emission lines for hydrogen. If you're looking at a helium lamp, these would be the energies for emitted electrons from helium, and so on. So you'll use the measured wavelength as a way to determine the change in energy when an excited electron falls back down to a ground state. And so we'll look at why that is a bit. So we use this type of model to think about energy transitions between different energy levels in atoms. And we're going to use the hydrogen atom for our calculations, and that is because the hydrogen atom is the most simple for us. So hydrogen has just one electron and just one proton, and so the interactions involved lead to much more simple calculations. And we're going to be given a known value of energy for the electrons in the first energy level and in the second energy level, and that will lead us to the ability to calculate energy for electrons falling down from higher energy levels, and we'll use N as the representative for the higher energy levels here, but it could be the third energy level, fourth energy level, fifth energy level, and so on. And we'll use the wavelengths for the emission lines to determine what that energy is. So this kind of diagram shows energy on the y-axis, and these lines represent the energy levels. And so the lowest one is the first energy level, the next highest is the second energy level, third, fourth, and so on. The reason we are not looking at the transition between the second energy level to the first energy level is that this is such a high amount of energy that it does not appear in the visible range when it emits a photon as it relaxes back down. Actually, that higher energy appears in the UV range, and so we're not able to see it in the spectroscope. However, the transition for an electron that was excited to the third energy level falling back down to the second energy level, we can see. It appears in the visible region. And that's also true for any electrons that fall from the fourth energy level to the second, fifth to the second, and sixth to the second. This is called the Balmer series. These are things that we can actually measure with our spectroscope. So you'll get a wavelength value for the sixth energy level to the second, fifth to the second, fourth to the second, third to the second energy levels. And these will be in order of the magnitude of their energy, i.e. the magnitude of their wavelength. Remember, longer wavelength is a smaller amount of energy, shorter wavelength is higher energy. So you would expect a larger number of energy levels to have a larger energy and therefore a smaller wavelength. So more likely things closer to a blue or purple color would correspond to more energy levels being relaxed. All right, once we actually have those values, we can connect like which wavelength goes to which transition. So we'll let 6 be n in for the value that we measure for whatever we assign as our wavelength d. And essentially once we have all of those points, we can determine the change in energy, and we will know like what energy level we're looking at based on how we assigned them, and we can plot these values. And we'll get a nice line, hopefully, and that will allow us to relate the energy level with the change in energy. And you could think about what the slope of this line would represent in reality, so what is m, and you could think about what b would represent in reality. And since b is a y-intercept, it's essentially when this line crosses 0 for 1 over the energy level squared. This would essentially happen at the point where n is equal to infinity. So what energy would be reached if you were to reach the infinite energy level? So this is a very conceptual experiment, but we'll hopefully be able to connect some of the measurements we make of light interacting with the hydrogen atom with energy levels involved in the hydrogen atom from a energetic standpoint.